Welcome, everyone, to AI on AI, the podcast where we unravel the complexities of artificial intelligence for both the strategists in the boardroom and the architects in the tech trenches. Today, we're diving deep into a fascinating paradox in how we fine-tune foundation models. Why does a complex, two-stage reinforcement learning process often beat simpler, direct methods, especially when, from first principles, it feels like it shouldn't? To help us unpack this, we have a fantastic panel. Welcome, our expert in AI strategy. Great to have your business perspective.
Thrilled to be here. This topic has huge implications for how we operationalize AI effectively.
Absolutely. And welcome to our expert in reinforcement learning, ready to get into the algorithmic weeds with us.
Thanks for having me. It's a subtle but powerful area we're discussing today.
We also have our expert in language models, who lives and breathes foundation model architectures. Welcome.
Hi there, looking forward to discussing the nuances of these models.
And rounding out our technical deep dive, our expert in theoretical ML, who can shed light on the fundamental principles at play.
Pleasure to be here. The why behind these empirical successes is always intriguing.
Finally, our expert in applied AI research, who brings insights from the front lines of implementing these models.
Hello, excited to ground this in some real-world observations.
Great, so let's set the scene. Expert in language models, can you briefly describe the typical two-stage fine-tuning process using RL, often called RLHF, versus the more direct, offline approaches?
Certainly, so with many of today's top models, fine-tuning isn't just a simple supervised task on a dataset of good examples. Instead, it's often this two-stage dance. First, you train a reward model, essentially, an AI critic on human preference data, like this response is better than that one.
And the alternative, expert in reinforcement learning.
The alternative, often called offline fine-tuning, tries to skip that explicit reward model training and RL step. Think of methods like DPO, direct preference optimization. They aim to directly adjust the language model's parameters to maximize the likelihood of preferred responses over dispreferred ones, all from that same initial preference dataset. It's like trying to teach the student directly from the textbook answers without a separate tutor.
So on the surface, the offline method sounds simpler, perhaps more direct. Yet the paper and a lot of empirical evidence suggests the two-stage RL process often wins. Expert in applied AI research, is this what you see in practice?
Overwhelmingly, yes. Across academic benchmarks and industry applications, that two-stage online RLHF approach, despite its complexity, tends to produce models that are better aligned, more helpful, and better at nuanced tasks. The paper itself shows this with their DPO versus online DPO experiments on summarization.
This is where it gets really interesting. Expert in theoretical ML, the paper points out an information theoretic conundrum. The reward model is trained on the same data, and on-policy sampling in RL doesn't magically create new human preference information. So, why the better performance? The data processing inequality suggests we can only lose information by adding an intermediary step like a reward model.
Exactly, that's the crux of the puzzle. If you use the same function class for both your policy and your reward model, and you have perfect optimization, the paper actually proves an equivalence. Theorems 2.2 and 2.3 show that, under these idealized assumptions, online RLHF and offline MLE methods like DPO should arrive at the same solution. It's like saying all roads should lead to the same likelihood peak.
So theory says it's a wash, but practice, as expert in applied AI research highlighted with Figure 3 in the paper, shows a clear gap. Online DPO, which uses an explicit reward model, outperforms standard offline DPO. What gives?
Well, the paper systematically investigates several hypotheses. For instance, H1 was that there's some intrinsic value to online samples, that getting feedback on what the current policy generates is inherently better. But the authors argue that since the labels are imputed by an RM trained on the same off-policy data, it's not new information. You could, in theory, do value iteration without sampling.
Then there's H2, the idea that offline methods fail at regularizing to the prior policy effectively, especially with limited data coverage. While that's a factor, the paper shows even when controlling for the regularizer, the gap persists, and methods like SIMPO, which don't explicitly regularize, still perform well.
I found H3 interesting, that online PFT is somehow an easier optimization problem. But the paper uses DPO for both online and offline experiments, so the optimizer is the same. The only difference is the data. They even tried prompt augmentation, nearly tripling the training data for online DPO, and saw almost no improvement, which argues against the idea that more redundant samples simply ease computation.
So if it's not just better regularization or an easier optimization landscape, what about the reward models themselves? Expert in language models, Hypothesis H4 suggests global RMs can be trained on more diverse data, or H5, that they generalize better out of distribution.
The paper tests this too. They created a more concentrated dataset using samples only from the SFT policy and still saw online DPO improve performance over offline DPO even with this narrow data. This makes it less likely that the advantage solely comes from the RM's ability to leverage wider data distributions than policies can.
And regarding H5 OOD generalization, the paper finds that while global RMs do seem to have better in-distribution validation likelihood, which correlates with better best-of-n performance OOD, it sort of kicks the can down the road. Why do they have better in-distribution performance in the first place?
This leads us to the paper's core argument, Hypothesis H6, the generation verification gap. Expert in theoretical ML, can you unpack this for us? It sounds like something out of a Gödel lecture.
Chuckles, it's definitely in that spirit. The idea, which has roots in complexity theory like P versus NP, is that for many problems, verifying a solution is computationally easier than generating one from scratch. Think about a complex math proof. Checking if it's correct verification is usually much easier than coming up with the proof yourself generation.
So how does that apply to fine-tuning LLMs?
The hypothesis is that the reward model acts as a verifier. It's easier to learn a relatively simple reward function that can distinguish good outputs from bad ones, even if the function class for the RM is notionally as complex as the policies. The RL process then leverages this simpler-to-learn verifier to guide the search for an optimal policy. Crucially, it constrains the search to policies that are optimal for these simpler verifiers. The paper calls this proper policy learning.
So if I'm understanding this from a strategic angle, we're saying it's easier to teach an AI to be a good critic of, say, a business proposal summary than to teach it to write a brilliant one from thin air, and then we use that critic to train the writer.
Precisely, the paper's abstract puts it nicely. The combination of the ease of learning the relatively simple RM verifier from the preference data, coupled with the ability of the downstream RL procedure to then filter its search space to the subset of policies generators that are optimal for relatively simple verifiers, is what leads to the superior performance.
Expert in applied AI research, the paper presents some compelling experiments to support this H6. Can you walk us through one or two?
Absolutely. One of the most convincing is when they deliberately tried to close this generation verification gap. For example, in Figure 10, they tackled a two-word summarization task. Here, the horizon H is very small, essentially a bandit problem. Generating a two-word summary isn't that much harder than verifying one. And lo and behold, the performance gap between online and offline DPO virtually disappeared. Online DPO offered minimal improvement.
And building on what our expert in applied AI research just said, they did something similar in Figure 11 by using Rugel score as the reward. Rugel, which counts word overlap with a reference, is a complex reward to model accurately. The verifier becomes as complex as the generator. Again, online DPO showed no improvement over offline DPO. It's as if, when verification isn't simpler than generation, the RLHF detour offers no benefit.
It's like that old saying, I may not know art, but I know what I like. The verifier RM knows what it likes, even if it can't paint the Mona Lisa itself.
Laughs, that's a good analogy. And the paper also points out that isomorphisms are not a two-way street. While you can mathematically define a policy from a reward and vice versa, the computational complexity of learning one versus the other can be vastly different. Learning a local RM, like DPO implicitly does, is akin to learning a Q function, which can be as complex as learning the policy directly.
This is fascinating. From a business leader's perspective, this generation verification gap idea resonates. We often find it easier to define what success looks like for a complex project, the verification criteria, than to lay out every single step to achieve it perfectly, the generation. If this RLHF approach is leveraging that, it could explain why it produces more nuanced and aligned AI assistance, which is critical for customer-facing applications or complex decision support.
So, expert in AI strategy, does this mean businesses should always opt for the more complex RLHF route, given its potential for superior results? Or are there scenarios where simpler offline methods are good enough?
Well, that's the million-dollar or perhaps billion-parameter question. There's a cost to complexity. RLHF pipelines are notoriously tricky to set up and maintain. If an offline method like DPO gets you 90% of the way for a specific, less nuanced internal application, the ROI for squeezing out that extra 10% with RLHF might not be there. It's a classic 80-20 rule consideration.
We've heard a lot about why RLHF might be winning, but expert in theoretical ML, I'm going to throw a bit of a curveball. The paper mentions, in the infinite data limit, H6 predicts that this gap should vanish. Why is that, and what does it imply?
That's a great point. The idea is that with an almost infinite amount of preference data, you'd have so many examples that you could directly learn the complex generator, the policy, to perfection. The simplicity, advantage of the verifier, reward model diminishes because you have enough data to map out all the complexities of the generation task itself.
And that's a practical reality. We rarely have infinite data. So, for the foreseeable future, techniques that cleverly manage the learning process with finite, often messy, data are going to be key. Learning a simpler verifier first seems to be one such clever trick.
Now I want to inject a moment of, perhaps, contrarian thought. Expert in AI strategy, you've been nodding along to the benefits, but is there a risk here? Are we, for instance, over-indexing on the complexity of RLHF when simpler wins are still on the table?
That's an excellent point, and it's my element of surprise for today, if you will. While we're all chasing state-of-the-art with these sophisticated RLHF pipelines, I sometimes wonder if we're overlooking massive potential gains from more foundational aspects. For many business use cases, the real bottleneck might not be the fine-tuning algorithm itself, but the quality and diversity of the initial supervised fine-tuning (SFT) data, or even the pre-training data.
Ooh, a spicy take. So, the human feedback loop is crucial, but maybe its primary win in many cases is more about guardrails and basic preference alignment than coaxing out an nth degree of subtle performance. Expert in reinforcement learning, how does that resonate with the RL perspective?
I see the point. RL is a powerful tool, but it's not magic. If the underlying task can be well specified by good demonstrations, SFT can take you very far. The RLHF really shines when the desired behavior is hard to demonstrate directly but easier to judge comparatively, or when you need to explore beyond the demonstration data to find truly novel, better solutions. But yes, garbage in, garbage out still applies, even to sophisticated RLHF.
And building on that, the isomorphic classes assumption from the theory is key. The paper uses the same SFT checkpoint and data for training policies and RMs. If your RM architecture or training allows it to learn simpler functions more effectively from the data than a policy architecture can directly, that's where H6 gets its teeth. If we design RMs to be inherently better at capturing these verifiable goodness signals with less data, that could be a huge lever.
This discussion about simpler functions brings to mind a bit of humor. Is the model essentially saying, look, it's way easier for me to learn what good looks like in your human-preferred summaries than to actually be that good from scratch without a guide? Sounds suspiciously human, doesn't it?
Laughs, it does. We all know people who are excellent critics, but perhaps not the best creators in that same domain. Maybe our LLMs are just reflecting a fundamental aspect of learning complex skills. As Einstein said, imagination is more important than knowledge, but perhaps verification is easier than both.
So looking ahead, what are the big research directions or practical implications stemming from this H6 hypothesis? Expert in language models, where do we go from here?
Well, one direction mentioned is using mechanistic interpretability to actually see if the circuits learned by reward models are simpler than those in policies. Another is developing RM architectures that are even better at representing human preferences, especially tricky ones like intransitive preferences, where I like A over B, B over C, but C over A. Current Bradley-Terry models struggle with that.
And from a theoretical standpoint, H6 suggests that for increasingly complex, long-horizon tasks, think multi-turn dialogues or truly agentic systems, the gap between online and offline fine-tuning might become even more pronounced. The generation task becomes exponentially harder, so a good verifier would be even more valuable. That's a testable prediction.
I also think there's work to be done on the RL side. If the RM is indeed simpler, how can RL algorithms most efficiently exploit that? Are there better ways to perform that reverse KL projection the paper talks about to translate the RM's wisdom into policy improvements with minimal loss or distortion?
For business, the implication is that investing in robust human data collection for preference tuning and reward modeling is likely to remain a key differentiator. It's not just about more data, but the right kind of data that helps build these effective verifiers. And as I mentioned, not neglecting SFT quality.
Expert in applied AI research. Any final thoughts on the what for practitioners building these systems today?
I think the paper provides a strong why for a practice many of us have adopted. It's not just voodoo, there's a principled reason RLHF often works better. It encourages us to think about the nature of the task. If it has a significant generation verification gap, lean into RLHF. If not, simpler offline methods might be perfectly adequate and more efficient. It's about choosing the right tool or perhaps the right road to likelihood.
This has been an incredibly insightful discussion. We've journeyed from information theory to practical experiments, from P versus NP to the nuances of training today's most advanced AI. It seems that while all roads might theoretically lead to likelihood, the path through reinforcement learning, guided by a well-learned verifier, can be a surprisingly effective shortcut in the complex landscape of policy space, especially when it's easier to judge than to create. A huge thank you to our expert in AI strategy, expert in reinforcement learning, expert in language models, expert in theoretical ML, and expert in applied AI research for shedding light on this complex topic. And thanks to our listeners for tuning into AI on AI. Join us next time as we continue to explore the ever-evolving world of artificial intelligence. This paper argues online fine-tuning excels due to a generation verification gap. This gap means reward models are simpler to learn than optimal policies. Reinforcement learning then efficiently finds policies for these simpler reward models. Advanced foundation models are often fine-tuned using a two-stage process. First, a reward model learns from human preferences. A policy is a system that generates text based on a prompt. A reward model scores the quality of this generated text. Then, reinforcement learning uses this reward model to update the policy. This online approach surprisingly beats direct offline optimization on preference data. Information theory suggests this extra step might lose, not add information. Under idealized assumptions, online and offline methods should yield similar results. These assumptions include using identical function classes for policies and reward models. maximum likelihood estimation, directly learns policy parameters from data. Reinforcement learning from human feedback is a popular two-stage online method. The researchers propose the generation verification gap explains the online advantage. Verification, like assessing summary quality, is often easier than generation. Thus, learning a good reward model, the verifier, can be simpler. It may require fewer samples or learn from simpler patterns. The reinforcement learning stage then searches for a policy optimal for this learned simple verifier. This effectively narrows the search space for the policy. Online fine-tuning becomes a form of proper learning over this constrained space. Offline methods tackle a harder, improper learning problem over all possible policies. Experiments showed online methods consistently improved summarization performance. Global reward models, which assess entire outputs, showed better learning signals. They achieved higher accuracy on unseen preference data compared to local models. When the generation verification gap was reduced, the online advantage diminished. This was tested using very short summaries, simplifying generation. It was also tested using complex, rule-based rewards, complicating verification. In these cases, online and offline methods performed similarly. Offline methods like direct preference optimization learn local, token-level reward structures. These local structures are akin to complex Q functions from reinforcement learning. Learning these Q functions directly from data remains a hard statistical problem. Global reward models capture a simpler, overall assessment of output quality. The mapping from these global rewards to policies is where reinforcement learning shines. This finding suggests focusing on learning effective, simple verifiers. Future research could explore reward model architectures and their complexity. Understanding this gap could improve fine-tuning for complex reasoning tasks.